Hello, this is Miraj Patel, and today we're going to be wrapping up Unit 5, and we're going to be talking about properties of ionic compounds and bonds, and then we're also going to just briefly review the other slides from this unit. And so here, again, ionic bonds are bonds caused by the transfer of electrons. And it's important to know it's transferred. So these electrons aren't really shared. Sharing electrons is something totally different, and that is covalent bonding, and that's what we'll talk about in the next unit. So, but ionic bonds are transferred because these two atoms are totally have different electronegativities. So one sort of hogs the electron. See, in this example, in sodium chloride, the chlorine hogs the electron while sodium is just there and it doesn't really have much of the electron. And this bond is important because it causes a tight crystal formation. So here in this picture you can see that the chlorine and sodium form a tight crystal when they're all packed together, and that is why uh, ionic bonds have these properties, and we'll talk about them in a few slides. And so here are some examples of crystals, and this all has to do with the bonding. So inside we have a bunch of little calcium and fluorine ions bonded together, and they pack so tight that they form crystals. And and it's because they're orderly arranged. And so here's another crystal, another one, and look how pretty they are. And this again all has to do with the bond structure and how tightly they're packed. And so here are the properties of ionic bonds that we have to know. And so uh, there are about 5 different properties. And again, the strong attractions form a 3D crystal lattice. And so here in this picture you can see that the chlorine and sodium form a nice tight cube. And here are the 5 properties. They have zero net charge, and the whole reason has a zero net charge is because it's an octet, and so the positive ion and the negative anion, positive cation, negative anion cancel out. So sodium has a charge of 1 plus, while chlorine has a charge of 1 minus, and that is why it cancels out. And then we have a high melting point, and high melting point has to do with these tight bonds. So if you think about melting point, you heat up a solid, and the solid starts to become energized and evaporates, sort of like water. So water is, in a liquid, it's all condensed like this, but these once it evaporate, these bonds have to break. So we have to put in a lot of energy to break these bonds. So that's why they have high melting points. And they're hard and crystal. They're hard and crystal like those, like we saw in those pictures. They were all crystals. And they are very brittle. So like any crystal, they are brittle and break easily. So, you can't put like a lot of pressure on these. And they're good conductors. So if you think about salt water, and if you ever gone to the beach and then there's a thunderstorm, everyone tells you to get out of the water, get out of the water, because the lightning or electricity from lightning easily travels through water. So if we have more ions or more ionic compounds in water or some solution, the better it can conduct electricity. And it's interesting that water by itself doesn't conduct electricity very well, but the elements and stuff in water, like salt and a bunch of other minerals, that's what makes water so conducive to electricity. So next time you go to the beach, just, and they tell you, oh, water conducts electricity, because they're thinking of the ocean. So just, you can tell them that it's now you know that it's the salt in the water that conducts electricity well, not necessarily the water itself. And so here's one question to see what you've learned. So which is true about ionic compounds? A. Typically soft and malleable. B. Poor conductors. C. Crystalline solids. D. Electrically neutral. Or E. Formed by sharing electrons. So here, first let's just find the correct answers, and then we'll talk about which ones are wrong. So which two of these answers look correct? So metals aren't aren't soft. I mean, ionic compounds aren't soft because they're crystals. They I told you about the beach analogy, like how the ocean has so much salt, so they are good conductors. And C is correct because they do form crystals. And D is also correct because we talked about how the positive and negative ions uh, cancel each other out, and that's why we have a balanced charge or neutral charge. And this one's not correct, and so let's just change all these statements to make them correct. So let's go start with A. They're typically soft and malleable. So what can we change to make it correct? We can change soft and malleable and make it brittle, because brittle is the exact opposite of soft and malleable. Brittle means just hard and breaks easily. So that's um, true about ionic compounds. And they this answer says that they're poor conductors, but in reality they're good conductors, and that's why you would get electrocuted if you went to the beach and lightning struck the water. And it's also important to know that they're good conductors when they're like dissolved. So like in the ocean, it's dissolved, or they could be melted down. And the last one, formed by sharing electrons, that describes covalent bonds, which we'll talk about in the next unit. And ionic bonds are formed by transferring electrons. So not sharing, but transferring. And so that's why one element usually hogs the electrons while the other one's just there. And so here we're just gonna quickly review um, how to name or how to write the formulas. And so here are the four rules of writing a ionic compound. So first we have to write the symbol of the cation first, or the positive ion, then the anion, and then we write the charges of each ion as a superscript. So we get this from the periodic table, and we tell the cation's charge by just looking at the row. So potassium is a cation. So we just look at the row, which is 1. So it's a +1 charge. And then oxygen is in 6. So 8 minus 6 is -2. So it has a -2 charge. And then we cross the charges, so just remember crisscross. And so we put these at the bottom of the opposite symbol. So we put the 2 under the K and the O, 1 under the O, and we just erase the charges. And that's how you do it. And a good way to check is you just you find the charges of each element, and you count the number of elements you have. So we have 2 potassiums, and potassium has a charge of 1 plus. So if 2 times 1 is 2, so it's 2 positive charges over here. And then oxygen has a charge of -2, and there's only one atom, so -2 is the negative charge. So the the positive charge and negative charge should cancel out, and you should just have a neutral charge. And here's one more example. So we have magnesium and nitride. So magnesium is Mg and N for nitride. And then we have a +2 charge for magnesium because in column 2, nitrogen has a -3 charge because it needs 3 electrons to get an octet. Then we cross the charges, and we get Mg3N2. And again, you can check. So magnesium has a 2 plus charge, so 2 times 3 is 6, so 6 positive. And then nitrogen has a negative 3 charge, so negative 3 times 2 is negative 6. So negative 6 plus positive 6, does it equal 0? And yes, it does. So we have the correct formula. And so here's a brief overview. So we have all the cations, which are positive ions, and then the anions, which are negative ions. And the reason why these are cations is metals have low ionization energy, so they can easily they can easily lose an electron. And so nonmetals are the opposite. They have a high ionization energy and a high electronegativity. So these can easily just take another electron, and it's also easier for these elements to take an electron because they're so close to getting 8. So they might as well get maybe 3 or 2 or 1 electrons versus these have barely any, so they can just easily just lose a few to get an octet. And then we have these transition metals, which we talked about. So transition metals, the special thing is they have two versions of themselves. So they have two versions, and but it's always important to know that they have positive. And so pretty much the special thing is that they have Roman numerals to tell you the charge, and you do the same exact thing. You just write the symbol, cross the charges, and so on. And also, if you have an ion or a formula unit, you can reverse the crosses. So instead of crossing down, you can just reverse it, so cross back up and tell the charges of each element. So that is how you can tell the charges of transition metals, by just back crossing. And then we have polyatomic ions, which are pretty much a fancy word for ions that have multiple atoms in them, but that you still treat them as one unit. So the same rules apply, but except that when you have multiple polyatomic ions, you just remember to use parentheses around the whole ion to tell you that you want the whole ion times 2, the whole ion times 3. And so you can, feel free to go back to the videos where I talked about polyatomic ions and transition metals, or the notation to see the full explanation. So I hope this helped you have a brief review about the Unit 5 about ionic bonds. So we talked about how ionic bonds are named, their properties, and the few types of problems like the ones with transition metals and polyatomic ions. So the next unit, like I said, is going to be about covalent bonding, which is the second type of bonding we didn't talk about yet. And I hope you have a good day, and we'll see you later.